grid AI scientist at RT. So RT is a French power grid operator, basically. And we'll tell you a bit more about our journey in open science and open research. But let me just quickly zoom on the industrial context, because it might not be familiar to you. So here is what a control room kind of look like today. It might be surprising to you because like electricity, you just press a button and the light is here. It's kind of magic, but actually there are still a lot of humans, human operators managing the grid in real time to make sure that we don't run into a blackout. And those are very highly trained engineers. In France, at least, they often come from the best engineering schools. So quite a complex work environment. And you can see that they have many different screens and applications to make decisions. So yeah, it's complex. It's not going to get any better for them because we're running in what we call the energy transition. So we have these targets, because of climate change, we need to limit emissions. We need to meet this zero emission target set by the European Commission in 2050. And to meet that target, there's a lot that needs to happen in between. Especially, we need to integrate massively renewable energy, so wind and solar. We're ramping them at a very high speed in the grid, but this has a lot of implications because those are intermittent renewable sources, and we cannot really control them. So we're moving from a world where we could control production, basically, towards a world where it's fluctuating a lot more. And also, it's becoming a lot more active because of us. We can have solar panels at our home. We can have batteries, electric vehicles, so we can interact a lot more with the grid. And also the system somehow is expanding a lot, at least in Europe, because initially it was more like national grids, but now it's a full European power system interconnected. So you can have wind power from Norway that comes into France or Switzerland, or solar power from Spain and Portugal that goes toward Germany. So a lot is happening in a short time frame now. And on the other side, also the grid itself is changing in nature. So we're hybridizing things. We have this digitalization. We have more automation also on the grid, and some new form of technologies as well. And the point is also that we have a hard time now to build new lines, new capacity for the grid. So basically, we have to be very smart to reuse the flexibility we basically already have in the grid, and this is quite difficult. So this is getting a lot more complex. If you ask, so you can imagine we'll need more applications, but if you ask an operator, what about one more screen? He might say, no, thank you, I've already enough. So we need to change something there. It cannot scale, right, in terms of decision making anymore. But the point for us is that humans remain key players. So there are some discussions sometimes about what about the autonomous grid. But there's so much criticality and so much responsibility there. And also the trade-off are not that easy when you need to make a decision and maybe cut, some region not to be able to supply electricity compared to another. So yeah, we need to keep them involved for sure. And so our target is more to now rethink the interface for decision making and move from this full supervision control room to a more unified interface for decision making. And now we're all familiar with kind of the concept of assistance given ChatGPT, etc. But this is not a ChatGPT. This is a lot more complex, right? So this is not about just chatting with an assistant. This is trying to embed the complexity of the information, the situational awareness, the flexibility of the grid within a more unified interface. And you need some properties also, such as robustness, adaptability, and trust. But yeah, one of the main challenges is to be able to solve congestions on the grid very quickly. Otherwise, you might run into a cascading failure. So that's about the context. And now I will guide you through our journey. But it first started, again, with an internal R&D project before moving to more an open science initiative. So back to the future. Actually, this vision, we already had a first working prototype some years ago, in 2017, where we had this more unified interface for decision-making that we call hypervision, where instead of having a very fragmented environment of supervision with some information, some recommendation, etc., just one-stop shop where you might have the alarms, the smart alarms, as notifications on the right, on the left in the field. You might have your timeline also on what you might need to anticipate at the top, and then you have the context field about what might be the problem at hand when you zoom on a task, and what might be recommendations on what you can do. And so here, basically, you see what we call a substation. So that's a physical location on the grid where we can connect power lines together and also reconfigure these connections. So here you see two buses, and the lines can be connected to any of those two buses, and then you can decide to couple to connect those two buses. So you can either work as one electrical node or two electrical nodes. So basically, you can change the number of nodes in the graph dynamically on the grid, which is a large flexibility, but a complex one as well. And so back then, we had already this interface working for the real grid, as well as a first form of AI, an adaptive expert system. So it's a bit more advanced than just hard-coded rules. And we had some also initial validation with the end users. So we thought, yeah, the future is almost there. But it was not deployed. It was replaced by a simpler supervision process for now because of those different aspects. So it was quite forward-looking, and maybe back then still less of a priority given also more stable context. So why change everything now? Now I think it's a lot more pressing. Yeah. Also, big leap in terms of operational practices and interactions, so change management is definitely something to look into, and we haven't worked a lot around that back then. We're lacking also strong internal sponsorship, so that was more a vision from a project manager who had a long history of building tools in the company, etc., plus also some enthusiastic end users. But at some point, if you change a project manager, which happened then, it might be a different story. And also you have to know that it's based on new technologies, requires some new IT skills and practices also. So in those industries, you cannot change things as fast as you might want, as you know, in Google or those companies. And back then also AI was starting to pop up a bit, but still there was some skepticism about, yeah, are you sure we should use? It's not very formal. It's data-driven. We don't really understand it. And there was no strong echo also from the research community in our power system community yet, and no objective benchmark also to show, yeah, look, at least we can thoroughly test things and it's doing better. And finally, no provider ecosystem. So in the end, we're not like tool developers. We're users. We don't have the capacity to just keep developing those tools and maintain them, etc. So we need some providers to actually take over. And we can also not rely on the GAFA. So we cannot go and ask Google do something for us. Yeah, it's not possible. We have to be independent with this regard. So somehow it was in the end rather a bit of a failure, but as you know, Churchill said, success consists of going from failure to failure without loss of enthusiasm. So let's try again. And what if we build it with the open community instead of internally? So That's the direction we took. And also we got a little push or impulse from our company because at that time, there was a big push to go for open source. We set up this Linux Foundation for Energy. So those are just example projects. There are many more, but and actually, Operator Fabric, you see, is maybe an industrial version of this interface you saw before, but without this intelligence behind. So that's still at least an outcome still of this project. So yeah, that really helped us because the company was saying, you can go for open source. It's not a problem for us. And basically, it's also opened a lot collaboration. Then we thought, okay, we'll still need to do research. And what is the current state of things? So we have the power system community on one side. We have the AI community on the other side. We had the feeling they were not really talking to each other. And that can be understood because they have different mindset. Basically, in the power system community, it's more about like formal optimization, equations and guarantees, engineering. It's more closed source also on working on small data. And in the AI community, it's a lot about being data-driven, a lot of open source also in the last 10 years. It's more computer scientist. And you want to just iterate fast, right, and prototype. So yeah, they were not talking and they did not really have the same ground. So one of our targets in this journey was really to have them talk to each other and attract the AI community. Because if you just take the AI community now, it's so large, so huge. I think it's a factor 100 at least in terms of size difference between our community and the AI community. So if you're just able to attract 1% of the AI community, it already doubles the forces for the new research on our problem. So that was a great incentive for us. And we started with a small first prototype, kind of similar to what Eric showed for Flatland. So what is the simplest version we could give to the community that they can really easily understand it, but also is already kind of complex. So here, you just see a small grid, but where you can already do some reconfigurations on the grid, etc. And basically, you see it evolving across a scenario, let's say a day, and some lines get congested, and if they're congested for more than 10 minutes, then they get disconnected, and then the problem is still there, and you might have a cascading failure if you do nothing. So here is basically an agent that does nothing, and that fails. And here we wanted to test the potential of AI to robustly operate a power grid in real time, and also giving some first operational constraints. So if you do something on the grid, you cannot just undo it just after. So you have to stick with that, and you have this time constraint to react to the problem. You cannot wait forever. And if you look at the number of, the action space is already huge on this small problem. Here is a number of topological configurations you can have just on this small grid. So if you go on a large grid, it's just a lot larger than the Go game, for instance. So it's really a lot harder than Go, not giving also the criticality of the problem. So that should be an incentive, right, for researchers to come try our problem. And now let me tell you a bit more about, so that was the initial step, and then we went into this journey, and we found some benefits definitely to that. So we released a first competition based on this small problem in 2019. It was more like a sandbox environment, a feasibility challenge to see, okay, how the community is reacting to our problem here. Are we seeing any interesting solutions before basically scaling up the problem? So the response was very positive. We actually saw both the AI community and power system community participating in this challenge. And the first winners of this challenge were a bit more from the power system community, but already a team that was working with AI a lot. So that was interesting. And as we scaled up the problem and added some more real-world features, such as robustness. So are you able to respond to unexpected outage on the grid? To adaptability, what if we integrate more renewables every year? So you have this distribution shift. Trust, what if you have to communicate with a human, so send alerts to say, okay, now you should really pay more attention because I might not be able to work properly on the grid. So yeah, and we had this competition at NeurIPS in 2020, actually Flatland also had one. That's how we connected also. And then we saw the AI community to actually took over this challenge and win. So we had Beidou from China who won this competition, for instance. And then we went up to this last competition last year. With Paris region, so it was sponsored. And before it was more for academia and researchers, this one was for startups and companies. So I will come back to that just a bit after. But some things we saw is that we attracted hundreds of participants, so that was very positive. And then it also brought some users, so very interesting. We had some papers. Now it has more than 200 citations, so it might not seem a lot in the AI community, but in our community, it's a lot. And we also, as assets, we got some dataset framework and baselines released, and that could be already reused, so that was very positive. But I will say the most important asset we built across that journey is this one, is a foundational digital environment that lets you actually run those scenarios with some data, with some physical simulator, and with an artificial agent or a human agent interacting with this environment. So that's kind of a digital twin, if you like. And most importantly, it was very standardized and modularized. So you can plug in any kind of data. So it can be synthetic data as we generated and used for the challenges, but it can also be real-world data. For the simulators, we have a long history in Power System community on building physical simulators, because before you do something on the real grid, you better validate it in the simulator to be sure it will work properly. The thing is that there is a galaxy of physical simulator today, and either a research lab or a power grid operator has its own simulator, and then if you want to work with someone, you have to use that one. And everyone is kind of redeveloping the same thing again and again because of that. So we said, no, let's just abstract it. Let's just say, plug your simulator, if you like it, into our framework, and then we'll just simulate the scenarios the same way. And finally, the agents, you want to have baselines to capitalize on the winning solutions, etc. So it's also important that it's modularized. So yeah, to have standardized interfaces and also the shared platform in terms of simulation data, algorithm metrics as well, really makes things a lot more handy, and you can build up on each other. And I would say we're not just aiming, let's say, about general learning. We also want to actually transpose that to the real grid with this framework. So yeah, just building a bit on what was said before, our target is to really just don't have, a gap at some point, at some tier readiness level, so tier 6, for instance. We want really to have a streamlined piece of research that goes also into prototyping and production. And when you look at the popularity of the framework, in the Power System community, it's the most popular framework for doing AI. So yeah, that's very interesting for us. And after competitions, you also get some benchmarks out of that. So you can do reproducible and systematic evaluation. So here we use CodaBench. So here are basically the results of the last competition, and you can have several metrics. So it's not only about one general metric, like accuracy, you're optimizing for. You're also looking at those other metrics, like how much renewables are you using? Are you able to alert the operator? How much time you take to make a decision, etc. So all of those metrics are important to us. And then what you get also out of that is state-of-the-art AI model. So we have now we had a team applying AlphaZero basically to our problems. So that was very impressive. They showed, so they have also a nice little interface to play with their model to just show how interesting this is. And they have some numbers, so this is saving up to 95% of costly carbon-intensive production redispatch, so that's very interesting. And what we were lacking, as I said before, was sponsorship. And to have this whole history of competition, then we could join with another initiative from the Paris region, which is their program AI for Industry, where they want some industrial partner to organize, to set up a challenge for the startup ecosystem to actually solve a problem together. And since they saw how complex and interesting our problem was, and also our capacity to organize such challenges, they came to us and we organized that together last year. And the benefit is that we got political support, basically. So we had the Paris region president, which was, she's a former minister, and also she was candidate for the last presidential election. And we got also our president just sponsoring and launching the event. And then you had the prize ceremony in the end in our headquarters. And for this challenge, the prize is basically a €1 million project to build a real-world demonstrator. And this is expected by mid-2025. And out of this, we also kind of map the possible ecosystem of companies and collaborators we could work with. So here are names of companies that participated in the challenge, other actors that interacted with us so far in the past, and also some collaborators. There are more actually, but INRIA was our main collaborator to start with, and then we had some collaborators from the power grid community, so other operators, research institutions, but also from the AI community. And then it also helps you to just become a reference in your community and continue building up this vision and what is needed to actually make progress on these problems with AI to have really something working in operations. So SIGRE is it's 100 years old association for worldwide cooperation among the power grid operators. So yeah, that's really a big echo room for our community. And I talked about AI, but I also said we need to involve the humans. And so we're also working on the interactions side. So once you have a model, it might not be totally appropriate to use as is for humans. So what is needed to reintegrate the full picture of AI models plus proper interactions for good decision making? And that's this other project we have, so also with other field domains, so trains, telecom, flight. And actually, this open source link is very fresh. It's from yesterday, so even my colleague was not aware of that. So yeah, the code is not there yet. It's a README, but it will be there in a few days. So you will be able to play with it. And what you see here is again a similar interface as the one we saw, in 2017, but revised a bit. And then you have assistance really from the AI model. Here on the right, you can pick up a recommendation and then see the effects. So solving an overload, a red line you see in the middle. So yeah, that's also very important to us, and we think we're making good progress on that as well. And as was mentioned, we also joined forces on AI for RealNet, so this European project. Actually, we're very happy to have it because the competition was fierce to actually have an accepted project. Only 4 proposals were accepted among more than 100 proposals. So it's also a very good recognition of the work we have done so far, both on the power grid side, but also on the railway side, and as well as air traffic management. So yeah, I hope we will achieve, again, very interesting work together there. L2RPN competition, so we're not running one this year. We also have to build this real-world prototype with the winning company. But in this project, there will be some competitions, and so L2RPN will come back next year, probably. And open research, so that was already a big open research initiative, but we thought we should just, transpose that to other tasks and kind of scale up this kind of initiative, given all the benefits we got. So we actually transpose this to another task, which is kind of close, but not exactly the same. It's about learning the physical simulation. And here we are having this project with other domains as well. So for instance, here we released this benchmark at NeurIPS for power grids, tire routing, airfoil design. And now we're running competitions for that. So ours on the power grid will actually start mid-April. So same, if you want to help and compete, it will be there very soon. So let me come to my conclusions. So first, I just want to reemphasize, I think, how important competitions and benchmarks were for us to have a successful journey. They're a great tool to accelerate AI advance and drive them towards real-world applicability. And also, releasing data sets, even if they are not the real data set, but very realistic ones that are representative of our problems. What are the important evaluation metrics to us for real-world application? And this fair comparison and reproducibility. So don't try to build the problem and solve it at the same time. Then you're just short circuit. You're just running into the solution rather than really setting up the problem, as Eric said. So that's very important, and it's quite a lesson. And I think it's a lot more rigorous in terms of science. And then when you try to design that across industrial domain, maybe we will come up with more foundational AI models, and that will really be a great achievement if that happens, because then it will be a lot easier for us as an industry to actually leverage AI and apply it. And of course, we hopefully succeeded to attract some part of the AI community. I think there is still more work to do on this part, but hopefully the European project will help. Some of the references are here. And just to reflect on the benefits I just presented. So here is a list, I think, of the benefits. So engagement of the communities, so both AI, but also human-machine interactions communities were very important for us. Being able to explain and democratize your problem, your real-world challenge, I think it was great. And actually, since the winners of our last competition comes from the AI community, I think we succeeded to that. We built this foundational digital environment, which is really the basis also for our internal research now to move a lot faster on a harder problem and with replicability. Benchmark and evaluation for objective comparison. So I said in 2017 we were missing that. Now we have it. So we can really say, okay, here's the difference between the different methods and where it works. We're able to build up on the results and on AI innovation. So we have this AlphaZero, for instance, state-of-the-art model that was showcased. Then you also become more reference in your community, so it gives more power, basically, to kind of develop this vision. And support and sponsorship, we're missing that, and now we have doors open to develop this real-world demonstrator and apply it. So that's great. And always try to seek for mutualization and generalization, because we're small industries still. We don't have the resources of the GAFA, etc. So really, when we want to go for these high-T advanced digitalization things with AI, you know how resource intensive it is, how much you need to build in terms of technical stack before having something really working well. So I think on this part, we should definitely keep joining forces across the industry to accelerate basically its deployment. And so we're happy to have now more common and sound playground for moving forward towards industrialization. And we also need to involve, again, more the end users in this demonstrator now. So yeah, thank you for your attention. Also to thank Isabelle Guillon. She was our great mentor across this journey. So if you don't know her, she is actually famous in the AI community. She was the inventor of the SVM back then. She was a general chair at NeurIPS, and she's a very big figure also to promote challenges and competitions for really advancing science. So yeah, thank you.